But let's work a little bit with surface area and volume. There are, as you might predict, a couple things we want to accomplish today. First of all, we want to become familiar with some of the common geometric formulas. Okay, there's certain ones that I will expect you to know, and certain ones that you just need to know. I'll point those out as we go. And once we know the formulas for those surface area and volumes, we want to use it to solve some application problems. So that's where we're gonna start. Now, first of all, how would you describe, just out of curiosity and to make you think about this, how would you describe a geometric solid? Okay, we're talking about, and I'm going to use one definition, a 3D object. Okay. Well, the way that we typically define it is that a geometric solid is basically a closed surface in 3 dimensions. Okay, it doesn't even have to contain anything inside of it. It can be hollow, and we can find the volume of it. But basically, a geometric solid is a closed surface in 3 dimensions. Now, there's a lot of types of solids, but one specific type of solid is a polyhedron. Poly, of course, means, I guess I've got it up there, many. Hedra means faces, and so we've got many faces as a solid bound by polygons. You might think of a solid that you're familiar with, in which every surface is a polygon. Simplest example probably is a good old cardboard box. In this case, you've got a polyhedra where every face is a rectangle. Okay, it certainly qualifies. Surface area is, as the name kind of indicates, and as you are somewhat familiar probably, surface area is just a measure of the total area of a solid surface. But there's one distinction that needs to be made between surface area and lateral area. Lateral means side. Lateral pass is not necessarily a forward pass. It's either a sideways pass or backward pass in football. But a lateral area is a measure of the area of the sides of a solid. That does not include the bases. Now, for a cylinder, the lateral area, think of a soup can. The lateral area is really just the area of the label on the outside of it. The top and bottom do not count in the lateral area, but they do count in the surface area. Okay, so we've established a little bit of terminology. Now what we're going to do is we're going to go look at the specific types of solids that we're going to work with and establish a few of their formulas for surface area and volume. The first one is a prism. A prism is any shape where you've got 2 parallel ends, they're usually called your bases, and sides that are parallelograms, usually vertical. Prisms are usually named according to the shape of their bases, so this would be a hexagonal prism. Hexagon ends. A box is a short name for what type of prism? Rectangular prism, right. The bottom's a rectangle. If you change the orientation, it's still a rectangular prism. And what we often call a cylinder is also a special kind of prism. It would be a circular prism. The ends are circles, so it's circular. Now, there are 2 types of prisms. One are oblique prisms, things that tend to lean. We will work primarily with right prisms, prisms that stand straight up. In other words, if I could take this stack of CDs and slide them over slightly so they were tipping, I would have an oblique prism. We don't work with oblique prisms very much. They're just not practical. Right prisms stand straight vertically. To find the volume of any prism, we just find the area of the base, whether it be a hexagon, a triangle, a circle, a rectangle, or anything else, and we multiply it by how tall it is. It's kind of like if you want to find the volume of a building, you find the volume of one floor and multiply it by the number of floors. And if it is in fact a right prism, which we'll be dealing with primarily, the lateral area is just the distance around the footprint or around the base times how tall it is. So the cylinder is the easiest one to think of. if you wanted to find the lateral area of a cylinder, what would you have to do? You'd have to basically find out the area of the label around the outside of it. And the label would be the length of the circumference, or the perimeter, times how tall it is. If I could unfold this box, tear it open, and hold it out lengthwise, how long would it be? It would be the length of the perimeter multiplied by the altitude. And it's generally true, of course, that the surface area is just the lateral area plus the bases. Okay? Well, let's do an example. This steel triangular prism weighs 1,300 grams, almost exactly, in fact. You'll have to take my word for that. 1,300 grams. It is 9.2 centimeters by 9.2 centimeters and 3.9 centimeters tall. And what we want to do is we want to find the density of steel in grams per centimeter, grams per cubic centimeter. Density is found by taking the mass of an object dividing by its volume. Okay, so let's go ahead and find the, well, we know the mass. Let's find the volume. Okay, we have roughly that shape. So the first thing we need to do is we got to find the area of the base, or sometimes you can think of that as the footprint of the prism. Okay, so that footprint is a right triangle. Shown in the picture that is a right triangle with a base of, triangle's base is 9.2 centimeters and an altitude of 9.2 centimeters. And so the area here, what does the area of that work out to? Should get an area of about 42.32 square centimeters. Okay, so now to find our volume, we know the area of the bottom, we can multiply it by how tall it is. So our volume is going to be the area of the base, 42.32 square centimeters times the height of the prism, which is 3.9 centimeters. And the volume of this steel prism turns out to be going to leave plenty of sig digs here. We'll round it off when we're done. 165. 165.048 cubic centimeters. Okay, everybody agree with that? All right, well then we can go ahead and find the density. Our density, lowercase delta, density is equal to our mass, 1,300 grams, divided by 165.048 cubic centimeters. And if you divide that out, we can round off to 2 sig digs here. It works out to have a density of 7.9 grams per cubic centimeter. 7.9 grams per cubic centimeter. There. Let's find the surface area. Well, we don't have to start from scratch. Surface area is going to include the lateral area and the area of the bases. We now know the area of the base. So I'm going to erase the density and gain some room here. Okay. Well, what is going to be the area of that side? 35.88. And you get that by multiplying the base of 9.2 times the height of 3.9. What is that? 35 point what? 35.88. And those are square centimeters. Now that also happens to be the same area as that side, right? Okay. So we've got two bases, which we know the area of. We've got these two sides, which we know the area of. What we've now found is the top, the bottom, this long side, this long side. The last one is the hypotenuse, the area of that face right over here. So we can't see it. It's on the back side of this, but we want to find that large face. How long is this side going to have to be? We're going to use the Pythagorean theorem. What does the length of this side work out to be? Let's see here. What is it? 13.0 what? 13.01. That's using the Pythagorean theorem. 13.01 centimeters. So the area of the third side, we'll call it the area of the back according to the picture because we can't quite see that back side there. The area of the back is 13.01 times 3.9. What does that work out to? 50.73. We'll leave a couple extra sig digs here. 50.73 square centimeters. So our lateral area would be 35.88 plus 35.88 plus 50.73. The surface area will also include the bases. So our surface area will be two of those plus the back plus two of the bases, 42.32. Two of the front plus the back plus the top plus the bottom. Anybody have that totaled up? 207. Let's see, how many sig digs can we keep realistically here? Yeah, we can really only keep two sig digs, so we'll call it 200, what was it, 207 point what? We'll call it 207.1. When we round that off to two sig digs, which is what we're really limited to, (210 centimeters squared). 207.1 or 210 when we round it off at two sig digs. And we found our surface area. Okay. Now, it's one of these few cases where we go from tougher to easier, but one very common, by far the most common geometric solid that we ever stumble across is the rectangular prism. Good old box, okay? Even though that's really just a special case of prism, you should recognize that to find the volume of a box, you don't necessarily have to remember that you're going to go ahead and find the area of the bottom and multiply the height. You just know that if it's a box, the volume equals length times width times height, okay? I mean, there's no point in making it more complicated than that. And one special case of a rectangular prism is the cube. And the cube, of course, is just the volume of one edge, which we call S, the side length, and we cube it. And we have the volume. If we want the surface area, we would find the area of all six faces and add them up. Well, let's take a look at an example. Circulation vent moves air at about 320 cubic feet per minute. This room, we said yesterday, is 16 by 28, but it's about 9 feet tall. How long is it going to take to cycle the air in this room? Well, this room is 28 feet long, 16 feet wide, and 9 feet tall. So the volume of this room, length times width times height, turns out to be 4,032 cubic feet. Now, 320 CFM, that really means 320 cubic feet per minute. That's what a CFM is, cubic foot per minute. So if we want to find out how many minutes it'll take to recycle all the air in the room, we can basically treat it as a conversion factor. Four thousand and 4,032 cubic feet. We don't want to know how many cubic feet it is. We want to know how many minutes that'll take. 1 minute will recycle 320 cubic feet. You're basically just performing a conversion. And it turns out that it'll take about 12.6 minutes. That's right. Yep, 12.6 is what it works out to, but we are limited to about 2 sig digs here because of our dimensions and the CFM rating. So we could say roughly 13 minutes clean out the air in a room. What is the lateral area of the room? Well, that also is a pretty short question. We're just going to determine, that's basically what's the area of the walls. If we were going to paint, ignoring windows and doors, what's the area of the walls? Let's take the perimeter, multiply it by how tall the walls are. That'll tell us our lateral area. So our perimeter, 28 by 16 the room was, so 2 times 28 feet plus 2 times 16 feet. That gives us a perimeter of, what is it? Not for a perimeter. 88? Perimeter's 88 feet. We need 88 feet of edging to go around the bottom. So our lateral area, we'll just take 88 feet of total linear wall length times how tall the walls are. And our lateral area works out to, keep putting my notes down here, 792 square feet. So that's our lateral area. Just as a side note, paint usually covers, depending on the kind of paint, 300 to 400 square feet per gallon. So our area is going to be less than that because of all the windows and the doors, but it'll probably take about 2 gallons to paint the room if we were so inclined. Okay, now even though it's only a special case, the next case that we want to look at are cylinders because they are so common. Hydraulic cylinders, the volumes of the hydraulic cylinders are cylinders or circular prisms. Ducting, piping, all cylinders. It's really just a circular prism. And to find the volume of a prism, we take the area of the base times the height. Well, for a cylinder, the area of the base is a circle, pi r squared. So to find the volume of the cylinder, we just take pi r squared times the height of the cylinder. Our lateral area is just the distance around the outer edge. That would be the blue region on that picture. We need to know how far it is around the outside of the cylinder. Pi times the diameter, that's our circumference, and multiply it by the height. And of course, to find the surface area, we take that kind of, I didn't notice this before, but that is pi times d times h, or pi times diameter times height. That sort of looks like pi LH. The d kind of runs in with the pi, but that's pi times diameter times height, the lateral area, plus 2 pi r squared. Why is there a 2 pi r square added on to the end for the surface area formula? Steve? Two bases, pi r squared for the top, pi r squared for the bottom. Top and bottom of your soup can. Here's what we've got. We just showed a little while ago that the density of steel, and that was accurate, by the way, the density of steel, typical steel, is in fact 7.9 grams per cubic centimeter. We want to know how much a pipe 12 feet long, 3/4 ID, and an 1/8 inch wall thickness would weigh. Well, forget about the weight for a minute. Let's just find the volume of the steel in this pipe. Now, there's really two methods to go about finding the volume of steel in that pipe. What are they? Think about them for a minute. If you see one way to find the volume of steel in the pipe, good. You see the other method. What's one way we could do this? Yeah, you kind of described both methods, Aaron. One thing that we can do is, are you talking about the circle or the cylinders? Okay. That's right. One thing that you can do is to find the area of the base. If you were to set this pipe on its end, the base would be a ring, right? Be the ring where that pipe sits. So we can find the area of that ring and multiply it by the height. That'll work. The alternative is to find the volume of the pipe as if it was solid, no hole in the middle, then find the volume of the hole in the middle and subtract it off. Okay? Well, let's take Aaron's method. Let's find the area of the base. That is to say, the area of, this is called an annulus. A ring is technically called an annulus. So, the outer circle is going to be pi times, let's see, what's the outer diameter for this pipe? 1 inch. That's right. The inside diameter is 3/4. The outside diameter is 1/8 of an inch in each direction, 1/8 of an inch wall thickness, and so our OD is an inch. So to find the area of the outside circle here, pi times radius squared would be pi times 1/2 an inch. That's our radius squared. Now we're going to subtract off the inner circle, which is going to be pi times, what's the inside radius going to be? 0.375, 3/8 of an inch. Now, the method that Aaron suggested, and the method we're doing this, is not the method that I used in the notes. I did the other method, so I don't have what this works out to. 0.25 squared, 0.35. What's the area of that ring? Did anybody get it? 0. Leaving plenty of sigdigs here. 0.3436. I'll let somebody verify that before we go on. Okay, so that's the area of that ring. Multiply that by how long it is. Now the length is given as 12 feet, so we got to make sure our units are the same. How long is this pipe? (144 inches). 12 feet, 144 inches. So our volume is going to be the area of the base. Times 144 inches, we got the volume of our pipe. That works out too. I think we should get 49.5. Is that right? 49.5 cubic inches. Okay, now to answer the question, that is, determine the weight in pounds. Well, we know that it's 7.9 grams per cubic centimeter. That's our density, but the units are all wrong. We're not dealing with grams. We want to find the weight in pounds. Technically, grams is a mass anyway, but we'll leave that, let that go. So our density, we got to convert that into a more useful unit. So our density is 7.9 grams per cubic centimeter. Let's get rid of that. Let's get rid of grams, go to pounds, so that we're in pounds per cubic inch instead of grams per cubic centimeter. So how can we get from grams to pounds? Let's go from grams to kilograms, where of course a kilogram is 1,000 grams. That takes care of that. Now we'd be in kilogram per cubic centimeter. We don't want that. Let's go to pounds. So 1 kilogram is 2.2 pounds. Whoops, there we go. So this would be pounds per cubic centimeter, but we don't want cubic centimeters. We want cubic inches. We want to get rid of the centimeters. They're in the bottom. We'll put them on the top. 1 inch is 2.54 centimeters, and we need to cube that. And if you convert that over, 7.9 grams per cubic centimeter, do that whole conversion. I'm going to leave an extra sig dig. You should find that 0.285 pounds per cubic inch. That's more useful for our purposes. We know how many cubic inches we've got. We want to know what the weight is in pounds. Well, now we're home free. What do we need to do to find the weight? Multiply our volume, how many cubic inches we have, by the weight per volume, weight per cubic inch. And so our weight is going to be 49.5 cubic inches times 0.285 pounds per cubic inch. Good thing we're done. We're out of space. What does that work out to? 14 pounds, 2 sig digs. About 14 pounds. Seems reasonable for a 12-foot long pipe. Fairly small. Well, next category of solid that we need to work with are the cones and the pyramids. They both follow the same general principle in that to find the volume of a cone, we take the area of the base times the height just like we would for a cylinder, but it's actually a third of that. And that's a result of calculus. So we take the height times the area of the base. That's the same as a cylinder, but we divide it by 3. And the lateral area of a cone, or a pyramid for that matter, is half the lateral area of a similar cylinder. Because it tapers, the area is only half. And so our lateral area will be S over 2 times the perimeter of the base. Now there's one distinction that needs to be made here. And that's the difference between S and H when dealing with a perimeter or with a pyramid or cone. H is how tall the thing is. How far above the base the summit or the peak of it is. S is what's referred to as the slant height. That's how far you have to walk if you were going to walk up to the top. Now, for a pyramid or for a cone, which one is always going to be bigger, S or H?
No, S.
S will always be bigger, okay? It'll always be shorter to go straight from the bottom up to the top than it will be to walk up one edge. And so the height is always a little bit shorter than S, what's referred to as the slant height. Now I got to tell you, if you're a math teacher and you're trying to think of things that are cone-shaped, there's not a lot of great examples. So, paper cups. On the golf course, that's right. Right by the tee for hole 9, you can load up on nice cold water from these little paper cups. Those little paper cups that you know you got to drink like 40 of to quench your thirst because each little paper cup holds one gulp of water. Well, there's a reason. They have a remarkably small volume. So those paper cups, after doing extensive research, I found out are about 3 inches in diameter and 3.5 inches tall. So the question is, when the golf course sets out that 5-gallon cooler, how many cups of water does that contain? Well, let's flip the cup upside down. We got to find the area of the base. Area of the base is pi times the radius squared. Now, if the cup is 3 inches in diameter, the radius has to be 1.5 inches, 1.500 inches. And that means that the area of the base is going to be, set my notes down. What is it? I just have the volume. 7.0685. We'll call it 7.069 inches squared. That's the area of the base. Our volume is going to be the height over 3. Well, we know that the height is 3.5 inches, so we're going to have the height over 3 times the area of the base, 7.069 square inches. And the volume of each one of these paper cups, assuming you fill it right up to the brim, works out to be, I have 8.247, leaving plenty of sig digs at this point, cubic inches. Anybody verify that? Okay, good. 8.247 cubic inches. That's what the volume of each one of those cups is. Well, how many cubic inches of water are there in that cooler? Okay, 5 gallons. The cooler has 5 gallons. There's 231 cubic inches per gallon. That's off your conversion sheet. That means that a gallon contains 1,155 cubic inches. So the number of cups we're going to have, we've got 1,155 cubic inches. Each cup is going to draw 8.247. And you're going to be able to get 140 cups of water out of there. Okay. We're going to bypass part 2 of this question just because there's a couple more examples that are of more importance that I want us to look at. How many square inches of paper are needed to make each cup? We would use the Pythagorean theorem to find out what S, the slant height of that cone, is. Then once we know the slant height, we could find the perimeter of the base and use our formula to find the area, the lateral area. If you take a cone or a pyramid and chop off the top, you end up with a frustum. Okay. The thing that's a little bit unusual about the formula for a frustum is that in order to find the volume, we need to know the area of the ends. Well, in the case of a conical frustum, we need to know the area of the top circle and the area of the bottom circle. That's A1 and A2 in that formula. H is the height of the frustum, not the slant height, but the regular height. So we take the height divided by 3 and multiply it by the sum of the bottom area, the top area, and the square root of the products of the area. Well, let's take a look at an example. This next one is also on your sheet. We have a 3.5 gallon pail. We want to make a 3.5 gallon pail. The top is 14 inches in diameter, the bottom is 10 inches in diameter, and we want to figure out how tall the pail has to be meeting those criteria so that it contains 3.5 gallons. We know that the volume has to be 3.5 gallons. We know that our dimension's in inches, so we need to take those gallons and convert them into cubic inches. Our volume turns out to be, if we convert 3.5 gallons, which is what we want, into cubic inches, we get 808.5 cubic inches, again leaving extra sig digs. So we know that's what the volume has to be. Okay? Now for our pail, we need to find A1 and A2. Doesn't matter which is which. According to the diagram, I've got A1 on the bottom, A2 on the top, so we'll just stick with that, but they certainly could be reversed. It's not going to change the volume. A2, the one on the top, is going to be, the area is going to be pi times, now what's the diameter of the top? It was 14 inches. So to find the area of the top, we're going to take pi times 7 inches squared. So A2, the top, turns out to be 153.94. A1, the bottom, is going to be pi times. Now the bottom diameter is 10 inches, which means the bottom radius is 5 inches. And the area of the bottom, A1, turns out to be 78.54. So we know A1, we know A2, and we know our volume. Now we can use our formula for Frustum to calculate what our height needs to be. I'm just going to scoot back so we've got the formula for a Frustum there. Our volume, 808.5, is going to equal our height, which we are trying to solve for, over 3 times A1 plus A2 plus the square root of the product. Now you want to solve for h. What would you do there? Work all that out. Divide it off. Multiply both sides by 3 to clear the fraction. And if you do that, we will not go through that algebra. Shouldn't have too much trouble with that. Clean up what's in parentheses, and then it's just a linear equation. H turns out to be, thank you, 7.08 inches. Now, how many sig digs are we allowed here? I think we are allowed 3. Going back to the original problem. Yep, 3 sig digs all around. So 7.08 inches should be the height of the pail. That's if we want it full right to the brim. Might be good to put an extra inch on there so the pail doesn't have to be completely full in order to hold 3.5 gallons. So we're done. You only need to know one dimension in order to find the area, surface area, or the volume of a sphere, and that is the radius. You want to know the volume? We take 4 pi times the radius cubed and divide it by 3. We'll have the volume. Surface area, 4 pi r squared. So, let's do one example involving a sphere here, and we'll be where we need to be. Again, after extensive research, I learned that the regulation size for a bowling ball, a regulation bowling ball can be no less than 26.98 inches and no greater than 27.02 inches in circumference. So if you're ever going to enter a bowling tournament, be aware of that. And you're going to use a homemade ball. A standard bowling ball is 27 inches exactly in circumference. So we know that we want to find out what the density of the ball is. We know what 16 pounds. We need to find the volume. What do we need to know to find the volume? We got to find the radius. We know the circumference, so we can find the diameter. We know that 27.00 inches, the circumference, is pi times our diameter of the ball. So dividing both sides by pi, we find that the diameter of a bowling ball must be, thank you, 8.5944. Plenty of sig digs here. Which means our radius is going to be exactly half that, 4.2972 inches. Now we know the radius. We can find the volume. The volume is going to be 4 times pi times our radius of 4.2972 inches cubed over 3. If you crunch that out, you'll find that the regulation volume of a bowling ball, ignoring the finger holes, is 332.4 cubic inches. Good up to there? All right, our density is weight per unit volume or mass per unit volume. So our density is going to be 16.0 pounds. And that occupies 332.4 cubic inches, which leaves us with a density of 0.0481 pounds per cubic inch.